Hey guys, thanks for joining to another Stack Exploder series. Uh, as Micah mentioned, my name is Jin. I'm one of the co-founders here, but today we have a very special day. We have our very own Jake, who's our co-founder and CTO at Saga, and Zaki Manian, who's an OG in the Cosmos space that I've been working with for a very long time, and so to
I,
talk
I
about.
disagree. I'm just an NFT influencer.
Okay, sure. Zaki, an NFT influencer that I have not worked for a very long time with. But really glad to have you guys here. And we're going to dive a little bit deeper into kind of the technical aspects of Saga. And so before we begin, though, let's do a round of introductions. So, Zaki, do you want to start?
Yeah, I'm Zaki. I have been working on designing blockchains for 10 years. Um, been a contributor to a bunch of different chains, including Cosmos, and still doing that. Also created the Slots NFT collection, which I think I'm also a protocol by Ingoyama. So wear many hats. Um, yeah, it's really exciting to be like I've been working with the Saga team on how this whole thing is built for many years, and it's super exciting to like. I think we haven't really like unpacked what makes Saga like a special, like a really unique ecosystem, like infrastructure tool for sovereign chains before, and so I'm excited to do this.
Cool. Jake, do you want to give a quick intro?
Yeah. Hey everyone. As CTO, founder at Saga. Prior to Saga, I've worked in just, I would say general tech, but heavily a focus on product. Had a product studio for a while. Worked on everything from mobile devices to embedded medical wearables and all sorts of fun stuff. Um, I have a bit of a research background as well. Uh, not as veteran to the space as Zaki is, but excited to have this conversation and appreciate you all for joining.
Cool. So let's get right into the deep end immediately. So, Zaki, you wanted to start this conversation with what makes Saga kind of special, right? So let's start from there, and we'll kind of follow. There'll be a thread that we'll pull, and then we're gonna just keep pulling.
Yeah, so I guess like we could like maybe start with like what is the market need, market demand source that Saga comes from, and then like what is it technically, which is for a very long time, there has been sort of this demand for sovereign chains. We've seen it from many different places. Um, everything from people who want to be able to just experiment with the blockchain design space to corporations that want to have their own sort of dedicated environment. Um, but having a sovereign chain was expensive, time consuming, all of these things. And there's like a lot of different infrastructure providers have spun up at one time or another to kind of address it, but to like sort of go after this opportunity. But Saga is like a really unique approach. So why don't we talk about like sort of like okay like Jin and Jake, like what are like the core mechanics and mechanisms of Saga?
Yeah, it's a good question, a good starting place. I think there's many ways to answer this, and I'm super close. I'm like on the map here, but I would say if stepping really far back, I think a realization for us and kind of one of our really biggest driving forces is that we want to commoditize the chain, um, the cost of the chain, even. If you think about any other network or even other Cosmos chains, there's always some notion of scarcity. So like if you're running on Ethereum, and Ethereum becomes congested, you're going to be stuck in a fee market. right? Like there's always this underlying assumption that blockchain space, which is really, a CPU executing some serialized process with some RAM, that somehow that is scarce. When in fact, CPUs and memory are things that we've been as a society great at building. So maybe it's stepping too far back, but I really do see a big difference for us and the way we look at ourselves in that regard. We look at building block space as a commodity, and how we actually execute this is interesting and worth noting here as well, which is because we see it as a commodity, we can do certain things a little different. For example, our token economics, or how we actually pay our operators, instead of them being driven by this premium scarcity type of model, our validators are paid for simply their operating cost. And their operating cost is running hardware, right, in a data center or co-location. And typically this hardware really doesn't change in cost per congestion on any network. That's a little different for RPC nodes, but let's just focus on consensus. Consensus is going to cost about the same under the covers on your operating costs, whether it's producing 0 transactions or full blocks. And so that's what we charge for, right? That is what we have people pay for. And this decoupling allows us to do things. Here's the punchline. Here's where I'm wanting to get to. It allows us to do things like you could launch a secured Cosmos chain that does nothing. It's a hello world chain. And this is not possible really on other networks. Especially with other proof of stake networks, you would need to have some type of token economics. You need to have some type of compensation to pay the premium for validators beyond their operating costs, because that is what's expected. You cannot simply just launch an empty chain elsewhere. So I know there's a lot of points in there, and we can drive into some of them, but maybe that's a little bit of a landscape. I can also jump into some of the kind of technical stuff of how we do this as well, not just the philosophy. But that's the first thing that comes to mind.
So maybe what's different about Saga than, let's say, launching a roll-up as a service?
Yeah.
That, like, I don't know whether or not you have to compare and contrast against one specific infrastructure technology,
Yeah.
but I think it's worth talking about, like, what are the pieces, what are the components, who are the players, who does what when a new chainlet launches?
Yeah, so I would, there's a number of ways to do this comparison. First off, for us, obviously, we're running proof of stake chains. Consider them as essentially a fully integrated chain. So in order to run a chain, you need to conceptually need a few things. You need to have consensus. Consensus needs to have a sequencing and order of messages and transactions everyone agrees upon. Needs to have execution, and then needs to have agreement upon the execution of those transactions. And it also needs to be available for future consideration and proofs to show that something happened on chain, and what I'm seeing as a light client, let's say, is what happened on chain. That's the proof part of it. So there's these different aspects, these different features that need to be somehow composed together to make a blockchain. In modular, in a roll-up, those things are separated, and that's fine. It's the intended design. So you might have in a roll-up, you have a sequencer, you have someone who's executing. That could also be the sequencer, but your sequencer could be shared. You could have your provers if you're producing ZKVM validity proofs, for example, or you have your auditors, or you have your DA layer, someone like Celestia that provides the coordination of what blocks are proposed, or historical blocks that were, would otherwise be served across the network. So you have all these different components that end up composing the things you need to actually have a chain. And for us, That's all integrated into a singular stack, right? And what is the benefit of this, as we see it at least, is it goes back to that previous point I was attempting to make, which is we can't have any type of scarcity in our system. And maybe it's hard to communicate this, but consider like the supply chain of a rollup. You have a rollup, and let's say you have a DA. Well, your rollup now relies, its cost to actually perform now relies on the cost of whatever DA layer or whatever shared sequencer that you're using. And the shared sequencer is shared, and the DA is shared. So the dynamics of your cost are driven by this premium market where if your DA layer gets congested, well, guess what? Your rollup's going to cost more. Or it might not work if you can't price in. And the same thing with your shared sequencer. And so for us, we have that completely decoupled. We don't have this problem because everything in our stack is driven by this commodity approach of just paying for an operating cost and not fighting over a synthetic scarcity. That does not have to exist.
Yeah. So when someone starts wants a chainlet,
Yeah.
Where do they go, and what's that user interaction like?
Okay. Yeah. Being very practical here.
Yeah.
The user flow. Yeah, I can get you there. The real simple. Right now, we have an application, a web experience, where a user can interact with this web app, obviously, and it's just a matter of filling out a few kind of required fields like the name, the tokens you want to have, the Genesis accounts that you want to launch with, the things that constitute the kind of what we call chainlet parameters internally, but they're the inputs to the configuration of your chain. And so you enter this in, and then there's a transaction that happens in, right now, Saga tokens. We can talk more about how that'll change in the future, but there's a transaction that happens to pay for the initial escrow of this chain. So this all happens in a web experience. It's a kind of like a single widget. You fill out an information. What it does, it fires off that transaction. It goes to our chain, our platform chain. Our platform chain maintains I'll go a little bit into the technical detail, just a little bit, maintains a chain directory. And these are all the chains that should exist and should be running. And then we have a controller in our validator stack that's watching that chain directory on chain and saying, oh, great, someone just launched a chain. And it will spin up the resources needed in its data center. And once those resources are up, the web application who's polling after this initial transaction, who's polling our service, will see that, in fact, all the components of the chain has launched. So that includes Block Explorer, that includes RPC, that, of course, includes all the validators who are involved in running the chain. So for the user, it's really just that input and wait, right now, maybe a minute, maybe 2 minutes, and then you're off to the races. You now have a chain that is completely EVM compatible. It's, in fact, running an implementation of EVM with your RPC endpoints, and your whole toolkit for developing on Ethereum should plug right in.
So from the operator point of view, does the validator have to do anything, or does this chain just sort of start running on their infrastructure autonomously?
It's essentially, if you look at any of your classic control layer orchestration, container type tooling, just the general pattern, it's about the same. We have a source that says, hey, here's the things that should be running. We have a controller that's constantly seeing what should be running, then asks the system. So right now we support Kubernetes, but this will be pluggable in the future. But asks the system, hey, do you have these things running? If it doesn't, then it executes reconciliation and attempts to restart those services that aren't ran. And that's it. So it's a large control loop. Now, of course, the world's a little more complicated than that. So you can run into issues like, a persistent volume is not allocated, or one of your physical nodes has gone down, and now there's a little bit of downtime as the control layer provisions the resources. But yeah, I mean, the complete intention, the design intention here is to have the lowest overhead because once again, I'll hammer and probably to everyone's annoyance, we really do want to keep these things to run as cheap as possible. And in order to do that, reducing operating costs and increasing automation will help us do so.
I just want to like sort of frame this for people about like how this translates into a different user experience from, because like we sort of be like the natural comparison is a roll up is like roll up architecture.
Yes.
So if you look at like what the roll ups as a service are provisioning today,
yes,
they're provisioning pretty much everything except for the data availability layer on just standard centralized cloud infrastructure.
yeah,
Your
that's right.
sequencer, your sequencers, your RPC nodes, everything is just spinning up on centralized infrastructure today. With and like decentralizing all of that is a task for the future. If you look at what Saga does today, Saga spins up block space production, uh, uh, RPC nodes, all of that stuff on a decentralized validator set as a sort of decentralized cloud running today.
Yeah. I mean, it's where yes, that's the design objective. And right now, I mean, for full transparency, the chainlets that run are running on validators that we operate as just a matter of getting to market incrementally or faster and developing incrementally. But yeah, the design and literally what we'll be doing in the next couple of months is rolling out the decentralized stack version. But yeah, that's right, Zach. I mean, honestly, life would have been a lot easier if we could just stop here and say, all right, we're a roll up running on AWS. It doesn't matter. Let auditors audit our system, and we'll use proving and validation techniques elsewhere to show that we're doing our job correctly. So for us, yeah, that's right. We're proof stake chain, so we need to have our validators, decentralized, otherwise defeating the purpose. So yeah, that is a distinct difference. But I guess the question would be, how's that translate? What does that mean to the end developer? Proof of stake chains, they have this nice feature to them where, to keep things simple here, the state that you see on chain is finalized quickly, right? So it's called its finality, and so you can trust the result of a chain execution within seconds. Whereas with rollups, of course, you have a different mechanism to trust state. You can wait for a challenge period, or you can wait for a proof, or you can run a full node yourself and verify the chain. And while that's all good and great, I think the story gets kind of complicated when we start talking about, let's say, 200 rollups that need to bridge to each other. There's this kind of cascading dependency of state that you have to address, and you can wait for challenge periods to pass to get there, or you can run full nodes for every single chain that has a dependency in this kind of like tree of dependencies, or this graph of dependencies of chains. Or you can do like what we do, which is run proof of stake chains that have finality within seconds. And so there's a certain kind of safety and comfort and ease of design and to a system like ours, that where we could have hundreds of chains that bridge to each other without really worry of those states being correct, because they're all under the same umbrella of the validators that run the system via our shared security model. So that, once again, that might be overly detailed, but it's I think something worth mentioning as well that's different, that would translate to the end developer between us and a roll-up as a service, let's say.
There's some buzzwords from our planning document that I want to know what they mean. Okay, so fair uptime. What is fair uptime?
Oh, nice. Yeah. This is interesting. So when you look at a proof of stake chain, you have a distribution of stake that each of the validators have. So let's say with our network, let's just take an example network. Let's say you have 100 validators, and the 100 validators have an amount that they've staked, and they have an amount that others in the community have staked with them. And it is, in fact, this stake that is what secures the system. If a validator cheats, well, they lose part of that stake. They lose part of this bond, if you will. And if you look at the distribution of stake in any of the networks, and maybe we shouldn't go into why, but like there's a reason why you end up with an exponential curve, a power law curve, where let's say out of that theoretical set of 100 validators, perhaps the top 15 make up 2/3 of all the delegation. And this matters for a proof of stake chain because it's the voting power that dictates, it's the accumulation of voting power that dictates when consensus passes. And so, if you have, let's say, like 15 validators out of 100 that constitute 2/3 of voting power, it's really only the 15 validators that you need. So what about the other, if you got 15 validators that represent 2/3 of the voting power, then you have this long, thin tail of 85 validators who have less voting power. And so the fair uptime really it's about scaling the requirement of the long tail of validators to the amount of delegation they have. So let's say, once again, that 15 validators make up 2/3 of the voting power. Throw in 5 random from the long tail to get, redundancy in case some validator within that 15 is down. You could increase that to where you get to 70% of voting power. And that set will be necessarily way less than 100, given how these curves tend to be. Once again, looking at our cost structure, the person who launches a chain, they're paying the operating costs of validators. So if there's 100 validators, that's 100x whatever it costs to run an instance of a validator. Right? And so if I have fair uptime, and so I'm only requiring 15 to 20 validators out of the set of 100 without making a security trade-off. Maybe I'm making a high availability trade-off, but I'm making a trade-off that greatly reduces that cost. So it's not 100x, now it's 20x. Another way of looking at this is you have one validator who has, let's say, 5% of the network. Let's say you pay them, their cut is $10 of your chain fee goes to them. Why would you also pay someone who has 0.001% of the network also $10, right? So the cost of the security should scale with how much security they're providing. And so that's the idea here, is that we have kind of a scheduling algorithm that will proportionally schedule chainlet execution requirements, or otherwise put, will not penalize a validator for being down if they're not in that time slice in which they need to be up, based off of the amount of delegation they have. God, this is super technical and in the weeds. I don't know how many of you are this close to proof of stake mechanisms, but that is the answer to that question, Zaki.
Okay, can you give me like a short, let's do like a 1 or 2 sentence version of that answer?
You're the worst ever. Okay. Yes. Instead of having 100 validators run your chain, we will run just the right amount to get us to the majority of votes we need to actually run that chain.
Got it.
And that's going to be way less. It's going to be way less.
What you're doing is, rather than over provisioning validator sets for the desired security, you're sort of just in time provisioning. And if validators go offline, you can bring online another validator to keep the chain going.
That's right. So another real simple way of putting this is, if you have 1/10 of the delegation that's totally staked with you, then you're running 1/10 the chainlets. Like chainlet hours of validator that's run, you'll be responsible for 1/10 of it.
That's really cool. Yeah. See, it was very easy.
Oh yeah, I know, man. Like I should have started there.
Fantastic, and that was a really good answer.
This
Both
is what I
answers
do
were good.
usually.
Oh, is
I
it?
distill down Jake's
Yeah, but
thought.
I'm enjoying going directly to the source. You got to go directly. You got to go to the fountainhead. Um, okay. There's a line in here: optimized IBC. What does it mean for IBC to be optimized?
Oh man, this one's cool. I'll try to keep it shorter. IBC. First off, IBC is a Cosmos native technology, although it can be applied elsewhere. It's really a set of kind of, it's like a framework for a secure framework for bridging, from a very logical standpoint, but there's implementation. Of course, we're using implementation. Implementation's used by others, very popular. But the gist of how these bridges work is with the proof of stake chain, you have validators, and those validators are the ones who sign off on state, as we know, kind of gone over already. But if you want to bridge two proof of stake chains, if you tell each other's chains who the validators are, then the short way of thinking of bridging is that any message that comes across, you could prove using a proof and a Merkle tree path and hash, a bunch of stuff. But if you know who the validators are from another chain, you can, through a couple of steps, prove that a message or a state did happen on the other chain. And so there's those two parts. You have messaging, and then you have like who are the authorized signers or validators of your peer bridge. Those two things are constantly happening. Yep. And so with IBC, that's a pretty chatty overhead. If I send no messages, that first part of keep me in sync with the validators and who the authorizers are, that process is pretty chatty. And so there's a constant overhead with IBC to keep that up to date. And the kind of aha for us is that, well, because all of our chainlets are using cross-chain validation, they all already know who each other's validators are because it is in fact their own validators. And so, if I have chainlets, 1 through 5, chainlets 1 through 5 each of them have an identical replicated copy of who the validators are as, chains 6 through 10. And so any two chainlets that you choose will have the same validators. So it's really redundant to continue to report who the validators are to chains that already know who the validators are, because they know that from CCV with the platform chain that is where the source of security is. So if you cut that bit out, what that allows you to do, and maybe like lightweight IBC, or maybe a better name is like lazy IBC, what allows you to do is send messages with the message, and of course update the state hash, and then have a path proof from that hash to that message. And you can use the validators that you currently have. I mean, there's some bookkeeping in here, but you can use the validators you currently have to prove that signature is valid. So the signers, the authority is the one that is allowed to prove that message and so be able to verify it. So that's it. Like all the chainlets have the same validators, so why are they all spending time sharing who their validators are with IBC?
The basic idea is that you're running a sort of bespoke version of the IBC protocol designed for the Saga environment that makes it sort of less resource intensive and more scalable within the Saga environment to run lots of IBC connections.
Yeah, that's right. This is still in works, but it is something that we have shared, so it's not a secret. But yes, that's exactly right. And the reason it works once again is just because IBC spends a lot of time talking about who each other's validators are, and every single chain has the same validator in our chainlets in our network. So why spend that overhead? Synchronizing validator voting powers when you already know.
I mean, I think that there's been like a lot of interesting innovations on IBC, on sort of IBC like protocols and various networks. This is a cool one though. What are edge nodes?
Right now, if you run a Cosmos chain, you run a validator node, and you'll run something if you're choosing this architecture, but you'll run something that protects that validator node, and those are the colloquial use here is sentry nodes. So you might have this architecture where you have, let's say, 3 nodes that are running your chain. Let's say you're running osmosis. You might have 3 osmosis full nodes that are exposed to the wider area network, the internet, and they expose their peer connections that allow for networking to happen and for all the magical communication stuff that a chain does. But behind them, just local on the local area network or via a VPN or what have you, protected, not accessible to the internet, is the validator. And so this is the Sentry Node architecture, SNA. This is a great way.
Okay, wait.
Yeah.
I didn't really get it.
The SNA, Sentry Node architecture?
An edge node.
Oh,
So edge nodes are like what RPC net. I mean, like that sound like the direct comparison I imagine is like RPC nodes in Solana, right?
there's a common architecture in Cosmos. If you're running Osmosis or the Atom Hub or any Cosmos chain, this is common in other networks as well. So it's not specific, Cosmos technology. You want to protect your validator. Your validator is the thing that's doing consensus. You obviously don't want to leave it open to attack. So what you do is you run these other nodes that essentially firewall and protect that hidden validator. Now the problem is with this architecture for us is that means, an example where we have 3 of these Sentry nodes that firewall our internal node, we would have to have 3 of these for every chainlet, and so increasing the cost. And the reason why we'd have to have 3 or whatever multiple of protection has a lot to, why it can't be a shared resource. It has a lot to do with the fact that, has everything to do with the fact that these Sentry nodes also run state and execution. So as a validator runs, it takes transactions, it executes those transactions to update state, and then does consensus to sign. Full nodes, these Sentry nodes do exactly the same thing. They just don't vote on consensus. And so this is an unnecessary overhead. So what we're doing is we're virtualizing these Sentry nodes to make them a shared service. And this is what our edge node is. And so what you can do is have a cluster of edge nodes, or even just one, but multiple chainlets can use the same edge node because these edge nodes don't maintain state. They don't execute state. They simply, they virtualize the validators is a way of thinking about it. So they hide the validator, but they communicate certain things that the validator needs to communicate to the rest of the other validators in the network, such as transactions and state sync stuff. But that's what the optimization is we're building a new kind of gateway that allows many chainlets to share a resource. And this is a pretty common theme in our infrastructure. So once again, we're constantly looking at ways to improve the deployment of these systems where historically that hasn't been a needed thing, because usually validators might run 1 or 2 or 3 or 4 chains, but not hundreds. So we are constantly looking for spots where the kind of service stack can be shared by resources to amortize costs, especially given that not all chainlets need all the throughput in your system all at once. So it's a pretty standard technique in a kind of architecture, system architecture, is to share resources. So that's one of our inventions that presently doesn't exist in the world, except for what we got going on, what we're putting together.
Yeah. So just to quickly summarize, the idea here is in a traditional context, each chain requires a independent and dedicated resource for full nodes to do these kinds of Sentry node operations for protecting the validators. And this is something that has existed. If you look at the Cosmos hub, there is a independent set of full nodes that are running that protects the validator nodes for Cosmos, and Osmosis has a set, et cetera, et cetera. And while this is nice if you have one chain to think about, when you have hundreds or thousands of chains to think about, running independent full nodes for each of these chainlets is not sustainable. And so the point of the edge node is to kind of smush them all kind of into one set of infrastructure so that we can get most bang for our buck, I suppose is the easiest way to mention it.
Yeah, that's right. And there's also some cool things we can do down the road with it. Because it is this kind of participating node that firewalls and protects our chains, we can actually kind of break apart parts of our chain as well into other services in our validators data centers, and kind of use the edge node also as kind of like a functional router to those components. So in other words, there's a bunch of like design wins that we get down the road that will further make our systems more scalable, and scalable here equals higher availability and more reliable and cheaper and so on.
Yeah, Jake and I talked about this a lot too, where the way that we think about validators is like, it's like the king in chess, right? It's, you got to protect your validators, but not every operations that the outside world wants to interact with our chain needs to go to our validators ultimately. So
that's right.
The edge node allows us to reroute some packets out of the validator's direct control and into infrastructure outside of it, essentially. So let's say, for example, I want to state sync. Like, I don't think I technically don't need access to the validator. I just need access to somebody who's running services that allows me to sync state, essentially.
That's right.
So you can offload that outside of this direct network from the validators and protect the king further, essentially. So
yeah, the validator has a series of let's call them like subservices. There's the validator that's kind of the service, but it has subservices that it runs that can be pulled from it. And if you can virtualize this distinction of these subservices, then you can maintain this like virtual validator as seen from the outside. So if you connect to an IP and port of a cluster that's running one of these edge nodes, it will be as if you're connecting directly to a full service validator, even though behind it, if you're sending transaction syncs, it might be going to a mempool that's a shared service instead of the subsystem of today's validator implementation, just as an example. So there's actually, honestly, that it's a big win for us. It's something I'm really personally excited about, but it's not something you see presently in these systems, as Jin said, because it just has not been necessary.
I got the download on what an edge node is, which is super cool. So it's a node that like does the functionality of a Sentry node, but it's not specific to like one chain, right? Like
that's right. It's virtual memory. The physical memory are the services behind it, and so it's completely virtualized. It looks like whatever validator it's virtually hosting on behalf of. Yeah. And services can be broken out this way as well. So the like reactor channel for the mempool can be an actual separate service and not have to live on the validators protecting behind it.
I mean, this is like, I'm really excited about this because, like, this is essentially one of the ways in which you fix like the Berachain testnet bug.
Yes.
Right. Like when you have like a few 100,000 users suddenly hammering on your RPC, and like sending lots of transactions. These bugs that have existed in Comet BFT for a long time sort of get you into the state. But this is an architecture I've like long advocated for in like sort of the standard Cosmos stack, and I'm like really excited that you guys have built it. I think it's like one of the coolest things.
Yeah, I mean, for as long as you conform to the P2P protocol, that's that network layer of the current Comet BFT stack. For as long as you conform to that, it doesn't matter who's actually doing the execution behind the scenes, right? So if you think of it as just at the protocol level, protocol in the old sense of the word here, for as long as you're compliant with as long as you're compliant with Comet BFT's P2P, it doesn't matter where that execution is actually happening. I mean, you can completely virtualize it and multiplex it and share it and so on.
Yeah, and another big benefit of this is as a operator of the infrastructure, you don't have to follow through like, oh, which chain has more transactions suddenly, so I have to start dedicating more resources into
Right.
like this side. You just kind of spray these like generic edge node everywhere, and you're like, oh, I need more. Then you just open up more of these edge nodes instead of trying to dive deeper into like which specific chainlet is suddenly having increased activity, right? And so this also ultimately simplifies a lot of the infrastructure operations as well. So there's so many benefits that come from this kind of architecture that usually is not really that necessary with a singular chain. But as we mentioned, where like with the Saga system, where you have hundreds of these or thousands of these chains floating around, individually managing each chain's infrastructure needs is a really difficult task for operators. And so trying to make and simplify that is kind of one of the main tenets of what we've been following through with Saga. So,
But like, what are the things that have historically made sovereign chain block space a scarce resource? Have been like, okay, like where does my RPC come from? Where does my validator set come from? Where does my liquidity come from? And like the set of capabilities of the Saga sort of ecosystem seems to like one by one address every one of those things. And I think that's like a very cool and unique set of capabilities.
We are product driven, so at the end of the day, we do incrementally go after all those blockers that prevent our user from launching a chain and doing it securely with availability and access. And without this, premium, you need a token economics model to be successful. Anyone should be able to run a chain, and it should be as accessible as launching the underlying hardware that runs these chains. There's not, I can't think of a reason why that can't be the case.
thanks so much, guys. I think we're kind of running towards the end of the hour, and so maybe why don't we dedicate just a little bit of time at the end for final thoughts, and then we'll wrap this up after this. Zaki, do you have any final thoughts?
Well, I mean, I think I kind of like gave my final thoughts right before this. But yeah, I mean, I think that it's been sort of an interesting question. Like there have been these gaps in sovereign chain infrastructure for a while, and we're seeing. I mean, so like we've talked about all of the amazing things that have been happening in Saga. There are amazing things happening, I think, in a variety of different places in the ecosystem that are all additive to each other.
Thank you, everyone, for letting me do a technical deep dive. I do enjoy doing it, although it's not always a practical conversation. We are, in fact, actually practical, and we do have a great team that will help anyone launch a chain. And the more people that do that, the more we can learn from, because like I said, we really do drive our technology decisions. Although that's what we primarily talked about, they are driven by actual use cases and by feedback from people who are actually using the technology. So we don't want to live in a bubble, and we need you guys to help us make sure that doesn't happen.
Thanks everyone for joining. I think today we kind of summarize a lot of things that are technical aspects of Saga that are unique, and some of the innovations that we're bringing to the space. And so hopefully you learned something. I learned a ton as well, as usual, talking to some of our co-founders. And so thank you very much. Jake was our co-founder and CTO of Saga, and Zaki, who disappeared. I don't know where his speakership went, but Zaki, who's a NFT holder apparently and enjoyer and influencer. So thank you very much, everybody.